Hi everyone, welcome back to day 16 of Advent of Code. Today's challenge is called Reindeer Maze, and I feel like this is a very classic question for DFS. Um, so today what we are doing is we are sitting and watching some reindeer Olympics in which reindeer has to compete for the lowest score in a reindeer maze. The S is the starting point, E is the ending point, and the reindeer has to go through the maze and find the end point. But it's not as simple as that. We can't just go there and find what the score will be to get to that place. Every time we take a step, the score increases by 1, and every time we take a 90-degree turn, the score increases by 1,000 points. So that means if you're going front and then you turn back, that will increase the score by 2,000 points. I think that is unlikely to happen since we won't be coming back, but we will be leading to the other spots which will require a lot of 90-degree turns. So we have to do that, and we have been given some examples. Like one of them is in this example: if you go straight up, then right, then up, then right, then down, then right, then up, then you get to this point, and this will give you a score of 7036, which is one of the minimum scores, one of the best parts. There could be others, which I guess is if you go down and then take a right, and then I think, yeah, I don't know, I'll have to calculate if I think about it, but yeah, so we have to find the best path. Let's do this. Alright, so this was a simple thing, but it required me to debug a lot because of the silly mistakes I made. I mean, getting to this part was kind of difficult. So what I was trying was I was doing a DFS, which I thought would work initially, but that was taking very long to get a result in our in our actual input. So I realized it's probably because we have a lot of dead ends when it comes to our actual input, and as it scaled, it was probably not the best algorithm to use. The better algorithm would be to use Dijkstra's. So I was actually dreading using that because I would have to build my own priority queue and all. So I thought this might work, but it's okay. It didn't work, and so in this case we modified the code a little bit here and there to fit in our priority queue and heapify, and then actually use the proper Dijkstra's algorithm. So this is what the priority queue looks like. Since we don't have, I think we have a library for this in JavaScript as well, but I thought it was more work to go get. Actually, I just wanted to build this. If you're anyway going to do it, so it's been some time and I wanted to know if I can still do it. So yeah, we built this, and so here we construct an object of our class, and then in that we have build a queue. For this queue, we have different manipulation methods. One of which is enqueue. This is a private method in which we will add a single point at a time. Then we have enqueue, which is multiple items. So when we can enqueue multiple items into this method, and it will enqueue it one at a time. So what this enqueue method does is it will check if the queue is empty, then it will just push it. If it is not empty, then it will check at which point it's supposed to insert it, and the splice method will do that. At whatever point the priority of the item that we have given is lesser than the priority of the queue item, it will insert this item there at that point, and it will mark this flag as true. And if this flag is not marked as true, that would mean that none of the priorities are higher than the priority which we are giving, which means it will be the last item. So we'll push that. Then dequeue is just dequeuing it like a general queue. This method is for length, and this was for me to visualize what items are there. So yeah, we've got this as an example, and this seems to be working for our smaller sample input, and it works for our larger sample input as well. Let's check for our actual input. Still a little time taking, but it works. At least it gives us a result. So let's try this. Okay, let's paste this. Finally, after a lot of work. Okay, so it shouldn't have been this hard, but it is what it is. Now let's see what the second part is. Okay, in part 2, we have to find some seats, since this is the Reindeer Olympics, in which the reindeers are running in a maze. We have to find seats such that they are in one of the positions which are a part of the best path. So they have marked these best paths with O, and these O represent a best path. So we need a seat which is in one of these O's. So there are 45 such tiles in this example and 64 such tiles in this example. So we need to find if there are any, how many there are totally in the actual input. So we just have to find out what are all the paths which are giving us the minimum score, and based on that find all the locations that they have used. Alright, let's do this. Alright, so we finally got the solution, which is kind of messy, but anyway, starting from the top, process input is the same, get map information is the same, get score is sort of different now. Here the priority queue, the set is the same, and we are just adding a new thing which is called lowest score and tracking set. So we're doing the same process, but if we reach the target point, we're checking if the lowest score is null or the score is lesser than the lowest score, which is not possible. It's usually equal to. If it's equal to it, then we'll just assign it, since we are also working with null here. If it is not, we will break, which means we are not getting the least value anymore, so that path is not the best score. Then we will add whatever path we got to this point in the tracking set which we are tracking here, so that'll keep track of all the positions for the minimum, like the least scoring path. Then we will continue. So we've added one more condition here, that if it's going up and it suddenly comes down, then we'll ignore that, so that we can save a lot of computation. And what else? Yeah, instead of just sending the old point, we are also sending the previous and the current previous items and the current item. Not the best way, but it was becoming very tiring to figure out a cleaner approach. So if this doesn't work with the actual input, we'll have to still look for the best approach for that. Let's see. Okay, we're getting 543. We are also adding 1 to the tracking set, since I'm initially not keeping a track of our first node, which is our starting one, which is empty here. Okay, let's see if this works. Oh, great. Damn, this was a good day, good challenge. It took me very long to solve it and a lot of learning. So I think this was one of the most successful advent of code days for me, because this was a lot of learning. It was not just applying whatever I already knew, but it was great. Cool. See you in the next day. Bye bye.